Here's the same circuit we were looking at last time. If we're talking about a short circuit, what do we mean by a short circuit in the first place? What does that suggest is happening? The path is shortened, not so much shortened in a physical sense. It's not like, because the thing is the shape of the wire doesn't matter at all. We don't really care what shape the wire is. But yeah, we're adding a wire with no resistance. We're connecting some points that weren't already connected by just wire. So for example, let's say we draw in an extra wire. Let's say we draw in a wire from, let's say from this point, make that thicker. Let's say we draw in an extra wire from this corner to this corner. We've just fundamentally changed the entire circuit by doing that. So that's going to change all the values we found yesterday. It's going to change the voltages in many locations. It's going to change all the currents. So we're going to have to rethink how a lot of these things happen. And I think part of the best, probably the best way to look at a short circuit is in terms of the voltages. Short circuit is adding an extra connection in the form of a wire with no resistance. Or let's say little or no resistance. So, because any wire technically has resistance. It's just that we're assuming the wire has such small resistance compared to all the other values that its resistance rounds off to 0. So if we have this wire with no resistance, effectively no resistance, let's see if we can rethink the voltages. If we start labeling voltages, let's say we call the voltage right before the battery. And of course, all these locations in this corner are at the same voltage because they're connected by wire. What do we usually call the voltage right before the battery? What would be, if we wanted to just assign a voltage to that, what would be a good label to call that? Yeah, let's call that 0 volts. And of course, it doesn't have to be 0 because voltage is kind of arbitrary, but it's usually convenient to call the location right before the battery 0 volts. And that's also often referred to as ground. Ground just means the location we're calling 0 volts. Traditionally, that means this point is connected to a wire that goes deep underground, which forces it to be at the voltage of the ground. But ground is just often used as an abbreviation, as a short, an alternate term for the location that's 0 volts. And if you see a symbol that looks like a wire with parallel bars that get smaller and smaller, this is the symbol for ground. This symbol just means that this point is at 0 volts. Then we have a battery. What does a battery do to the voltage? Yeah, we get an increase in voltage. So this point, and not just this point, but this entire region, all these points connected by just wire, those are all at some higher voltage. And since this battery adds 98 volts, we're taking 0 volts plus 98, so this voltage will be 98 volts. So this corner, this region is at 98 volts. However, we then go through a resistor. What happens to voltage when you go through a resistor? Yeah, we get a decrease in voltage. And we can't really tell how much it's decreasing until we know the current. But we can say that we're dropping to some intermediate voltage, some voltage lower than 98, but of course higher than 0. So this is some lower voltage. But again, not just that point, but also any points in this region. Because what do we know about any points connected by just wire? If you got 2 points that are connected by wire, what do you know about their voltages? They got to be the same. So you can imagine this property of being at this specific voltage is sort of spreading out along wire. Any points connected by just wire. So these points are all at the same voltage up to the resistor, because we can't cross over the resistor. But also along this short circuit, all these points are also at that same intermediate voltage. And so is this location and all of these locations. All these locations along just wire have to be at the same voltage. So all these locations are at the same, I'm just going to call this medium voltage. We don't know how much yet, but some intermediate voltage. So we now have at least, we know there's only 3 regions, maybe this corner also, we don't know yet, but there's 3 regions where we have very low voltage, very high voltage, and this whole zone here is now some in between medium voltage. And the very important thing about this whole region being all the same voltage, what do you notice about resistor number 2 here? If we were to write out our usual Ohm's law for resistor 2, our usual delta V, what's the delta voltage for any resistor? Our usual formula for delta V. Yeah, negative IR. And what's the voltage difference that resistor 2 is getting right now? What's the difference between the voltage before resistor 2 and the voltage after resistor 2? Right, 0 volts, we get no voltage. Yeah, they're the same. Because since resistor 2, the one end of the other end can be connected by just wire. Any 2 points connected by just wire, same voltage. So this is something very important to look for. If you can draw a path from one end of a resistor to the other end of the resistor without going through any resistors, just going through wire, that resistor is getting no voltage drop. Essentially, yeah, it's not being used. It has no voltage. And if the voltage is 0, then the current also has to be 0. So this is one of the most important results of a short circuit. In any short circuit, that's going to be probably connecting one end of a resistor and the other end of the resistor with just wire. And note that the same is true for the other path. Resistor 3 and resistor 4, if we imagine that path as just one big resistor, the beginning and end of that path are at the same voltage. So that means this path gets no current at all. And since they get no current, we can ignore them. We can say that these resistors don't have any current at all, so they may as well not even be there. So this gets no current. This also gets no current. Can current still flow? Yeah, we do still have a complete loop, right? From the battery, we've got current flowing. Let me make that a different color. We've got current flowing through the battery. The same current flows through resistor 1 because they're in series. And now where can the current go? Yeah, current can pass through this wire, even though we get no current passing through resistor 2 or resistors 3 and 4 because those are shorted out. And then current can continue this way through resistor 5, and that's a complete loop. But notice that this whole circuit is now just one complete loop, since no current at all goes through these other branches, since they've been shorted out. And we could then calculate how much current that is, because now these resistors are just connected in series. There's only one single loop. So what's the total resistance here? Right, total resistance, 5 ohms. And now if we just have a single loop with effectively a 98 volt battery and a 5 ohm resistor, how would you find the current? Yeah, we could use delta V equals negative IR, and therefore I equals delta V over R. I'm going to ignore the negative here just because we're looking for absolute value anyway. The voltage provided is 98 volts. The total resistance is 5 ohms. So 98 over 5 would be Is that 19 point something? 19.2? Does that look right? 19.6, right?
Yeah, 19.6 is correct.
Okay, so that's the new current. This loop is getting 19.6 amps of current, which is way more than it was getting earlier. I think earlier we had, was it 9.8 amps? No, that's not right. 10 amps. Anyone remember what the current was from last time? It was a lot lower than 19.6. I remember that. But the short circuit effectively makes the current flow much faster. Because by bypassing these, what have we done to the total resistance? How does this total resistance compare to what we found earlier? If you add in, yeah, it's lower, right? Anytime you add in an extra path, and adding in an extra path in parallel, because this extra path is effectively in parallel to this path and this path. Anytime you add an extra path, you're making it easier for current to flow. In fact, if you add a path with zero resistance, you're making it much easier for current to flow. So making it easier for current to flow, lowering the total resistance, is going to increase the current through the battery. So this is typically the effect of a short circuit. Any short circuit, any extra path, is going to completely eliminate any resistor, any paths that it bypasses. This essentially provides an easier bypass. That means current doesn't even have to flow through these other paths. So we've got a bypass that completely deadens out these paths. If these are light bulbs, for instance, they just go dark. But it also means that much more current is flowing through the rest of the circuit. The parts of the circuit that do still have current get more current because the total resistance is less. So if R1 and R5 were light bulbs, what would we observe about those light bulbs? Yeah, they're going to be brighter. They're getting more current, so they're going to be brighter. And the other resistors that got bypassed are going to just go completely dark. The problem with short circuits in many cases is that if you have, like, let's say R1 and R5 were very low resistance and R2, R3, and R4 were much higher resistance. If you bypass the very high resistance stuff and all that's left is very low resistance, what does that suggest about the current? Like, let's say R1 and R5 in total were only like 0.01 ohms. Yeah, we're going to have a much higher current. If R1 and R5 together were like 1/1000th of an ohm, 98 divided by 1/1000th would be 98,000 amps. And that's ludicrously high. So if you short out the only parts of the circuit that have significant amounts of resistance, and all that's left is just wire with very low resistance, a large voltage applied to an extremely small resistance means a lot of current. And yeah, that's the problem with this, that wire is not invincible. The wire is going to melt at some point. So the usual result of an accidental short circuit, an unplanned short circuit, which might happen if there's some uninsulated wires that accidentally touch somewhere in the circuit. Usually what happens there is the wire is going to get really hot, and either one of the resistors that's still in the circuit blows up. That would be a burnout, which basically just means that that resistor is gone, leaving a gap, and that immediately causes the current to stop because there's no longer a complete loop. Or maybe just one part of wire melts and breaks. Worst case scenario, in like a house circuit or something, worst case scenario would be if it heats up so much that something catches on fire. So this is often the cause of electrical fires. If there's some uninsulated wires that touch, causing a short circuit, a bypass, then you're going to get enormous amounts of current, and the wire heats up, and maybe something catches on fire. But even if nothing catches on fire, whatever is the weakest point in the wire is going to melt through and break. And as soon as that breaks, the circuit stops completely because there's no longer a complete loop. And so this would be, you just get a blackout throughout the entire circuit, that everything would go dark. So this happens sometimes in house circuitry. If you've got, if you plug in an appliance that's got some sort of melted wire inside that allows current to just go right through without any resistance, then you get too much current flowing and something's going to break. But we can prevent that from being too much of a problem by building in this idea of fuses. Have you seen what a fuse is? A fuse is basically just a piece of wire that's deliberately weaker. Specifically, a deliberate weak spot in a contained area. A contained and known area. Typically what you have is like a little panel in the wall that opens up, and all the important circuits in the building go through this panel. And at the point where they go through this panel, you have the wire goes up to an open space and then out of the open space. And in that open space, you just plug in a fuse, which is typically just this glass capsule with a weak wire made out of lead or something with a lower melting point. So that means we know that if there's a break, it's going to occur in the weakest spot in the wire. The idea here is we're deliberately building in a weak spot so that if it breaks, we know where it's going to break. If you get a short circuit, you get too much current flowing, the whole wire heats up, but the fuse is what's going to break first. So the fuse breaks, it's in this glass vial, so the melting wire doesn't get on anything else. It doesn't set anything on fire. So it's safely containing the problem. And also you now know where it is. Instead of having to open up the walls and dig through everything and find where did this wire break, you know it broke in the fuse box. So you open up the fuse box, look around with a flashlight, figure out which fuse has broken, pull that out, replace it with a fresh fuse, and then the fuse breaks again because you didn't actually fix the problem. But if before you replace the fuse, you figure out where the short circuit was and remove it, then when you replace the fuse, everything should work fine again. So that's really what a fuse does. A fuse is just this deliberately designed weak point in a known safe location, so that if there's a short circuit, it doesn't cause any serious damage and it's easy to replace. Any questions on that so far? And then a circuit breaker is a related idea. Circuit breaker is, I guess you could say, a more advanced version of a fuse. More useful in a lot of cases, though fuses are sometimes more useful in other cases. A circuit breaker, instead of a weak point that's going to break, a circuit breaker is a switch that can turn off and on and automatically turns itself off using a magnet if there's too much current. The idea is you build an electromagnet into the switch, so that if the current is flowing too fast through the electromagnet, it pushes a bar up and turns off its own switch. So a current with a circuit breaker automatically turns itself off if the current goes above a certain value. And then once you notice that and fix the problem, you don't even have to replace anything. You just flip the circuit breaker back to the on position and everything should work. So that's what the circuit breaker panel in any building with electrical wire is all about. You have all the important circuits in the building passing through that box, and each one of those circuits has a switch that automatically turns itself off if there's too much current. Any other questions on those topics? The short circuits, fuses, circuit breakers, anything like that? All right, then let's take a look at the exponential decay stuff as well. And I think for this, the marker board is going to make a lot more sense. What are some situations you've seen so far that involve exponential change or that cause exponential change? Yeah, decaying radioactive isotopes. If you've got some sort of, some form of uranium, for instance, or plutonium, where the atoms are unstable and they're going to decay over time. And the reason that leads to exponential decay, let's say you've got a whole bunch of atoms. Let's say uranium. The decay process is kind of random in the sense that if you're looking at any individual atom, you can't really predict when that one atom will decay. but you can give probabilities. You can say over this period of time, there's a 50% chance that this one will decay to a different type of, to a simpler type of atom, or a 50% chance that it won't. And if the probabilities are known, then even though the individual atoms are not predictable, the cluster of lots of atoms becomes very predictable. For instance, if you go back to those coin toss problems we were looking at in 7A, if you toss one coin, you can't predict it. It's going to be heads or tails, you don't know. But if you toss 1,000 coins, what would you expect? If you're just flipping 1,000 coins, what would you expect the results to look like? Yeah, 50-50, or pretty close to it. Probably not exactly half heads and exactly half tails, but close to it. The same is true for these uranium atoms. If you know that over a certain period of time, which is called the half-life, there's a 50% chance that this atom decays, we don't know if that individual atom will decay in that time, but we know that over the course of that period of time, about half of the total atoms will decay. So that means every half-life, every one of these periods of time, half of the atoms will decay. And then one half-life later, we'll have half of what's left. One half-life later, half of what's left after that, and so on. But this means that the rate of change, the rate at which atoms decay, depends on how many there are right now. If you've got a lot of atoms, they're decaying very fast because over a certain period of time, half of them decay. If you've got only a few atoms, they're decaying very slowly because only half of that small amount decays in that period of time. So the result here, the big stepping stone here, is that the rate of change, how many atoms decay over a period of time, is proportional to how many atoms there are right now. Specifically, over a certain period of time, half of what you have right now will decay. But they're proportional. The rate of change is proportional to the amount now. This is really the thing that all exponential change situations have in common. The proportionality, the behavior that leads to exponential change is anytime you've got a system where the rate of change of some value is proportional to its value right now, that's going to lead to exponential decay. And we can write this as an equation. Rate of change, how do we usually write the rate of change of some quantity? Yeah, we can write this as a derivative. Let's say we've got some quantity y, where y is just some value that's a function of time. If the derivative of y with respect to time is proportional to y itself, this is the behavior we're talking about here. If the rate of change in y, how fast y is changing, is proportional to y itself. And this shows up in a lot of situations. Another one that's very common is population growth, for instance. Assuming that the population has unlimited growth, that there's no constraints on not enough resources or not enough space or anything like that. If you've got a population that's free to grow as large as it can, then the rate of change would essentially be the birth rate. And the birth rate, all other things being equal, is going to be proportional to the population right now. Larger population is going to tend to have a larger birth rate. So this also has the same sort of behavior. Population growth, assuming no limitations like lack of resources, is going to follow this sort of behavior too. We also get this in many cases of fluid flow. Not all cases of fluid flow, but a lot of specific situations. One common example is if you're draining a tank. Let's say you've got this tank of water with a spout at the bottom. And we've got some water here. If you take a look at pressures, what do you know about the pressure at the top?
It's equal to atmospheric pressure.
Yeah, that's atmospheric pressure. And let's say we're using gauge pressure here. So we'll call the pressure of the atmosphere 0. But then you go down through some water, specifically some water with, let's say, height h. What would be the bottom? What would be the pressure at the bottom here? If we treat this as a standpipe, the pressure, not the height.
It would just be like if you called that 0.1, it'd be P1 plus pressure atmosphere.
Well, we're treating the pressure of the atmosphere as 0. We can use gauge pressure here to simplify things. So pressure of the atmosphere is 0. But generally, what happens to pressure if you go down through some water? Yeah, we should get an increase in pressure. And how would we calculate how much the pressure increases? What's the type of energy density? Yeah, we could use the Bernoulli equation, right? What type of energy density is changing here as we go from top to bottom? Yeah, potential energy density. So our Bernoulli equation would involve a delta pressure term and a rho g delta y term, adding up to 0, because even though this is flowing, I think if we assume that the hole at the bottom is very small and the general cross-sectional area is very large, then we can assume that there is essentially no motion in this region. So that means our delta pressure is going to be, let's say we're going from bottom minus top. So the high pressure minus 0. Because if we're talking about gauge pressure, we can treat atmospheric pressure as 0. Plus density times gravity times height here minus height here. That's height 0 minus height h. So simplifying things by getting rid of the zeros, we get pressure at the bottom plus rho times g times negative h equals 0. So that means pressure at the bottom is just going to be rho gh. So that's our pressure at this point here. But what about the pressure just past this leak, just past this spout? Right, we're back to the atmosphere, which we're calling pressure 0. By the way, this gauge pressure idea, the idea of calling the atmosphere 0 pascals, is very much like what we've been doing with electrical circuits, calling the point right before the battery 0 volts. There's no reason we have to call it 0 volts. It's just a convenient reference point, and then we measure everything else from there. Gauge pressure is the same idea. The atmosphere is not no pressure at all, but it's a reference point we're using. We're calling the atmosphere 0 pascals and then measuring everything else from there. So when we say the pressure at the bottom is rho gh, we don't mean that its actual absolute pressure is rho gh. We mean it's rho gh above and beyond the atmospheric pressure. Any questions on that so far? And then if we compare these 2 points, what's changing from, let's say we're talking about like right before the spout to right after the spout. What's changing from here to here? We definitely have a difference in pressure, right? There's a rho gh versus 0. So from here to here, through the spout, we've got a delta pressure. Let's assume the spout is horizontal, so we don't have to worry about height. So if the spout is horizontal, we don't have to worry about height. If we're comparing like this point and this point, we would want to consider velocity. But let's say we're talking about the border zone between water that's essentially not moving and water that is moving. In that case, we don't really need to consider velocity so much because we're talking about a point on the border between moving water and stationary water. But what is probably going to be limiting the flow through this narrow region? What makes it difficult for current to flow through a narrow pipe? Why can't it just all flow out at once? There is a difference in area, but there's no difference in area between this point and this point. We're assuming these are both part of this flow pipe here. So what is making it difficult for current to flow? Why can't the water just all flush out at one instant? Yeah, this has resistance, right? This narrow pipe has a significant amount of resistance. So we want to include a negative IR term. So including the negative IR term, this is really what's preventing all the current from just flushing the water out in one instant. The resistance makes it difficult for current to flow, and that adds this time delay. But if we fill these values in, delta pressure, we know pressure here is 0. So if you think of this as final minus initial, 0 minus rho GH. We could then divide both sides by negative R and get current is negative rho GH over R. But the thing is, the current, what is current changing? How are we defining current in the case of fluid flow? Why would which one be negative? The term on the other side of the Bernoulli equation is generally negative IR because we're talking about a decrease in energy density. As current flows through a pipe, it's losing energy density because of the friction. So that means the IR term is going to have a negative on it, representing the fact that we're losing energy density. And note that these, that ends up just canceling out the negative on the negative rho GH, because the delta pressure final minus initial would be 0 minus rho GH. You could also interpret this negative as meaning that current flows from high pressure to low pressure. We've got a high pressure zone inside the tank, a low pressure zone outside the tank. So current's going to flow from high pressure to low pressure. So that's a good way of interpreting that negative in the negative IR. The negative just means current is flowing in the direction of decreasing energy density.
In the last part of that equation, where you have I equals negative rho GH, wouldn't the two negatives cancel out?
Oh, for this one, yeah, those ones do cancel out. Sorry about that. Because we're dividing both sides by negative R. Sorry, I thought you were talking about the first one here. So yes, the negatives do cancel out. We get current equals rho GH over R. But what is current? What's actually flowing here? Or how would we describe how fast it's flowing?
Volume flowing per second or per time.
Exactly. This is volume over time. Current is change in volume. And I'm going to write this as a derivative over change in time. So how fast volume is flowing is rho GH over R. And we can modify that also. The thing is, the volume changing causes the height to change also, because as volume leaves this tank, the height is going to decrease, which means this is not a steady state. Steady state would imply that the current flows at the same rate the whole time. But as current is flowing, the height gets lower. Less height means a slower current. So that means the height is going to decrease more slowly. And then less height still means the volume is changing even more slowly. So it's going to get slower and slower and slower and slower. In fact, if we were to graph this, if we were graphing time versus height, it starts off at some initial height. Large height means very fast current, which means it's draining very quickly, steep slope. But now there's less height. A smaller height means a slower current, so it's going to be changing more slowly, less steep slope. And now we have even less height, so that means the current is flowing even more slowly. So it's going to be slower and slower and slower, approaching zero. But the thing is, the closer it gets to zero height, the slower the current flows. So we end up with an asymptote. It's getting slower and slower as it approaches less and less height. And what sort of graph do we get here? What does this look like? Where have you seen this sort of graph before? Yeah, this is exponential decay. Because this idea that the rate of change is proportional to the amount now, here we have the rate of change in volume, which influences height, is proportional to the height right now. Ideally, we want to write it in terms of derivative of the same function that we have over here. But we can actually do that pretty quickly. Because how do we define volume in the first place? Or how do you calculate the amount of volume? Yeah, volume can be written as area times height. So we have d area times height dt equals rho gh over r. And is the area changing as the height decreases? Does that change the cross-sectional area? No, cross-sectional area is the same throughout, right? So that means A is a constant, and a constant multiplier can be factored out of a derivative. So that means we just have A times dH dt. If we divide both sides by A, we get dH dt equals rho g over AR times h. That is, the rate of change in that function is proportional to the function itself. This automatically leads to exponential decay, or exponential change anyway. The reason it's decay instead of growth, we actually need one more thing in this equation. As current flows, does current flowing make height increase or decrease? Right. As current flows in the positive direction, that actually makes the height decrease. So we should really say the change in volume is involving a negative height. That is, as current flows, it makes the height decrease. That's a change in the negative direction. So we need an extra negative in the derivative. We could also just multiply both sides by -1, so we end up with this formula. That how quickly height is changing depends on what the height is right now. More height right now means a faster change, but it's a change in the negative direction. What's going on is height is decreasing. So we need a negative to make those signs match up. And then the rho g over AR, density times gravity over area times resistance, this is just a constant of proportionality influencing how fast it's changing. So for instance, denser fluid and stronger gravity would make it drain faster. Wider area or more resistance in the spout would lead to slower change. But this still in general follows this pattern. Derivative of the function is proportional to the function itself. Any questions on that so far? So let's see if we can actually solve this idea of the derivative. We have dy dt is proportional to y. That just means dy dt equals some constant times y itself, whatever function y happens to be. So let's write it in that format. Dy dt equals some constant, which we usually call lambda. Doesn't really matter what the constant is. We just usually call it lambda, like you mentioned, times the function y itself. Also, since we're talking about usually exponential decay, we're going to put in a negative here so that it's already there. So let's assume that the derivative of the function is some negative constant times y itself. So we're assuming lambda is positive, and we're putting a negative here to make the result negative. So that's the core idea. We're assuming that we've got some function that's decreasing, and its rate of change is proportional to how much there is right now. Just like the water draining from the tank, just like the uranium decaying radioactively. And this also applies to certain electrical situations that we're going to see later. The idea of capacitors is going to follow the same pattern. And also heat flow often follows this pattern. If you've got a hot object surrounded by cold air, heat's going to flow. But the rate at which heat flows is proportional to the difference in temperature, how much hotter the object is than its surroundings. So that's a change in temperature as time passes, and how fast the temperature changes is proportional to the temperature difference right now. So heat flow also often follows this pattern. In general, anytime the value of the object right now, the value of the function right now influences how fast it's changing, that's going to follow this sort of pattern. But we can actually solve this. This is what we call a differential equation, an equation with a differential in it. And we can solve this using a technique called separation of variables. Usually, how would you undo a derivative? What's usually the opposite? Yeah, an integral, right? We would want to integrate both sides. We can't integrate both sides yet, though, because if we integrate this with respect to t to cancel out the derivative with respect to t, we'd also have to integrate this side with respect to t. And we can't integrate y with respect to t yet because we don't know what y is. But what we can do is this idea of separating the variables. The separation of variables involves moving everything with a y to one side and everything with a t to the other side. So what we're going to do is we're going to divide both sides by y to get the y to the side with the dy in it, and also multiply both sides by dt. That cancels out the dt in the denominator. So what we're left with is 1 over y dy on the left side, and then on the other side, the y's cancel out, we just have negative lambda dt. So we have separated the variables. We moved all the y's to one side, all the t's to the other side. And at this point, we can now apply an integral sign to both sides. And now we're just integrating a function of y with respect to y and integrating a constant with respect to t. Anyone remember what the integral of 1 over y is? Integral of 1 over the variable. Yeah, that's the logarithm. This is going to be natural logarithm of y. And negative lambda is just a constant. What's the integral of a constant? Itself times, itself times the variable. In this case, times t. So this will be negative lambda times t. Also, since we're looking for all possible solutions, and this is an indefinite integral, we don't want just a solution. We want all possible solutions. We should also include plus some constant. So negative lambda t plus some constant. So we've now gotten rid of the derivatives and integrals. Those cancel each other out. And all that's left is an algebraic equation instead of a differential equation. And the integral of 1 over y introduced this logarithm. How can we get rid of the logarithm so we just have y equals something? What's the opposite of a logarithmic function? Yeah, this is where the exponential comes in. The reason why we get an exponential function is because we had to divide by y to separate the variables. And when you integrate 1 over y, you get a logarithm. And now an exponential will cancel out the logarithm. So raise e to the power of both sides. Because if these two things are the same, then e to the power of each of those things will also be the same. On the left side, exponential and logarithm cancel out. So we just get y equals. And then on the right side, we've got an exponential with addition inside. We can split that up. If you have e to the something plus something, how would we split that up? How do you split up addition inside the exponent? If you had something like e to the a plus b, yeah, that can be rewritten as multiplication. E to the a plus b is the same as e to the a times e to the b. So we can split this up into e to the negative lambda t times e to the c. But the thing is, if c is just some constant we don't know, then e to the c is also some constant we don't know. So we can replace e to the c with some other constant, let's say capital C. So y equals some constant times e to the negative lambda t, where lambda is specifically the multiplier on y in the original differential equation. So for instance, in this case, lambda would be rho g over ar. So we could say, without even going through this process again, we could conclude that h is going to be e to the negative this whole constant times time times some other constant. So this is a universal rule. If this is your differential equation, if you know dy dt equals some constant times y, then y has to equal e to the power of that constant times t times some other constant. And we can even figure out what that constant is by plugging in values for t and y. What's the easiest t value to use? Yeah, if you plug in 0 for t, e to the 0 is just 1. So that means c is the y value. Specifically, c is the y value at time 0. So we can just mark that as y sub 0. That's our conclusion here. In general, if you know that the derivative of a function, the rate of change, equals some constant times the function itself, that always automatically leads to the function being an exponential function. Specifically, e to the power of that constant times t times the initial value, the starting value of y. So we can even fill that in here as well. Without even going through all the separation of variables and integration stuff, if you can get your equation for the situation into this format, derivative of a function equals a constant times the function itself, then you can immediately jump to this result, that the function is e to the power of that constant t times the initial conditions. So this is a very powerful result. Anytime you know that a function looks like this in terms of its behavior, anytime a function behaves like this, you know the function is this sort of exponential formula. Any questions on that so far? So as you're going forward, as you're looking into the stuff about heat flow, the stuff about fluid draining out of a tank, stuff about capacitors, when we get to capacitors later on in electrical circuits, look for opportunities to write out situations in this format. Whatever formulas you've got, Bernoulli equation, loop rule for circuits, heat flow, whatever, as long as you can rearrange it so you just have derivative of a function equals some constant times that function, you can use this fact and jump directly to the exponential conclusion. Any other questions on that? And by the way, this is going to involve a lot of manipulation of rules of exponents and logarithms like this one here. If you want some practice on that, just the general math involved, go to math.ncheese.org and click on Physics 7 Math Review. I've got a bunch of worksheets there for, I think the ones you'd want to focus on specifically are the one on exponents and logarithms and the one on solving equations. The first page of that solving equations one is all about solving exponents and logarithms in equations. So take a look at those math review worksheets. Feel free to bring those into office hours if you have any questions, and I will see you next time.